So next we're going to look more closely at changes to climate and what has been happening in recent centuries and what has been happening over a course of many thousands, if not millions of years. So we'll take a look at the data on how the Earth's climate has been in the past so we can compare it with how it is in current days. We'll also look at what is the evidence that climate change is actually occurring. And if we're convinced that climate change is occurring, what is the evidence that the causes of climate change are anthropogenic or human caused? And I point you to this website. This is an active link, and it's also posted separately on Moodle. The website has been put together from NASA, which is an organization which has gathered a great deal of data from all around the world and put it together in a nice up-to-date package. And I encourage you to take a look at the site and see what the current situation is and the evidence that they provide. So first of all, how do we know what the concentration of CO2 and the temperature has been millions of years ago? So here we have a graph from the NASA website. From current days, going back in years before present, so 50,000 years ago, 100,000 years ago, 200,000 years ago, all the way back 400,000 years ago. And you can see that on this axis, the y-axis, we have the change in temperature compared to the 1950s. We compare it to the 1950s because even though industrialization certainly began in the 1800s, if not before, or took off in the 1800s and started before that, the 1950s was the time period in which a great deal of global industrialization took place and more burning of fossil fuels took place. So we're looking at whether temperature has increased compared with present times or decreased compared with 1950, I should say. And you can see that it fluctuates over long periods of time. There are upticks and downturns, and it's quite a bit of variation. But how do we even know what the temperature was all those years ago? Humans weren't around, and even if we reach a time period where humans were around, they weren't carrying around thermometers in the cavemen and recording the temperatures on the cave walls. That's all been very recent. So there are three major ways that the temperature of long ago has been determined through studying ice cores, ocean sediments, and by making biological and physical measurements such as leaf shapes. And looking not only at each of these individual methods of determining temperature in the past, but comparing them to see whether ice cores come up with the same graph as ocean sediments, which come up the same graph as biological or physical measurements. So first let's look at ice cores. So for many, many years, glaciers have formed by having a layer of snow come down, and in that snow there are little pockets of air. And then as the next season of snow comes down, that snow turns to ice, and the air pockets are trapped, the gas pockets are trapped. And you continue on over time and have layer after layer after layer of ice formation with little pockets of gas trapped in it. So the gas trapped in this part, the deeper part of a particular ice core that's sampled, is older than the particular source of the particular slice of an ice core here, which would be relatively younger, and so forth. And so scientists have been able to determine by making a slice in these ice cores that are drilled into the glaciers, thawing it and determining the amount of certain gases that are present in the atmosphere over each of this period of time. So that's an indirect measurement of temperature over thousands of years. A second way, other than the chemical analysis of ice, is changes in species composition. So some species have been around for many centuries, millennia, such as cockroaches. But we have an even more ancient species, or genera, actually, of protist called Foraminifera. And Foraminifera are marine organisms that have hard shells, and these shells resist decay after death. And so sediments have built up for millions of years of these Foraminifera. An example of Foraminifera are the White Cliffs of Dover. Those are simply the remains of these organisms that lived in that area for millions of years ago. And anyway, different species of Foraminifera still exist today. And these species, there are different species of this genera which prefer different water temperatures. So when we see that same species, say 1 million years ago, or actually more in this case, 200,000 years ago, and it's a species that currently prefers warmer water, and we see another species that prefers, let's say, cooler water temperatures, then it gives you an idea of what the actual ocean temperature was at the time these layers of Foraminifera were formed. One of the advantages of using this biological method of species composition is that thousands of samples can be obtained, and the more samples you have, the stronger the data. A third way of determining temperatures from long ago is by analyzing leaf shape. If you recall from when you were studying biomes, trees that have needles instead of broadleaf, so coniferous trees that might be found in the boreal forest of Canada, have needles. And those types of trees are found in typically colder temperatures. And you don't find those so much in places like Florida. You find more broadleaf types of trees as you move southward in the northern hemisphere. And by analyzing fossils of various leaf shapes, it can be determined what the approximate temperature would be in that area when that fossil leaf was alive. And by putting all of these pieces together on one graph, if you have the same indicators of chemicals present in analysis of ice as you do in species composition, as you do in plant leaf shape and other forms of doing this, then that strengthens the data. Okay, let's talk for a minute about Earth's changes, orbital changes. I'm going to put up a bunch of stuff here. So, we know that in the past, the Earth's climate has changed. It's gone up and down. And some of the reasons that are hypothesized or to cause these changes are Earth's orbital changes and solar output changes. So if the Earth orbits more in one way, from round to elliptical, or if the solar output changes, that will result in natural changes to the Earth's climate in the past. So let's take a quick look at that. There are a lot of words on the slide. You do not need to learn them. I simply want to point out so you have a concept of the complexity of looking at climate change, and so that you understand that some of these natural changes that have occurred in the past are not occurring now. So scientists know that ice ages came and went cyclically, and they were able to study why that was. One reason is something called eccentricity. The Earth circles the sun in a flat plane. It's as if the spinning Earth is also rolling around the edge of a giant flat plate with the sun in the center. When the shape of the Earth's orbit or the plate, changes from a nearly perfect circle to an oval shape, it does so in 100,000-year cycles. A very definite change in orbit every 100,000 years. Next is the concept of obliquity. That is that the Earth is tilted on its axis, and the angle of the tilt varies slightly between 22 degrees and 24 degrees every 41,000 years. But that variation does have a significant effect. Another concept is precession. So not only is the axis, which tilts, slightly change, the axis can wobble toward and away from the sun, and it does so every 19,000 to 23,000 years. So then there was a scientist named Milankovitch who looked at these three items, the orbital variations in eccentricity, obliquity, and precession, and he predicted the point in time in which ice ages would peak, and that would be every 100,000 and 41,000 years. And then there would be additional blips every 19 to 23,000 years. So he used a mathematical equation to derive this prediction. And in fact, the paleoclimate record shows that there are peaks at exactly those intervals. Ocean cores showed that the Earth passed through regular ice ages, not just the 3 or 4 recorded on land by misplaced boulders and glaciers that were glacial deposits, which we're familiar with. But there were at least 10 in the last million years, or about 100 in the last 2.5 million years. So in another screencast, we'll look at current changes versus historical changes.